Section 4.3, Maxima and Minima. The main focus of this section is to find the absolute or global extrema of a function f of x. We'll let f be a function defined over an interval I, and we're going to let c be a value inside of I. We say that f has an absolute or global maximum on I at the value c if f of c is greater than or equal to f of x for all x and I. In other words, we say that a function f has an absolute maximum at c if f of c is the largest value our function can take on within this interval I. On the other hand, we say that f has an absolute or global minimum on I at c if f of c is less than or equal to f of x for all x and I. So the local minimum is the smallest value our function can take on. One thing to keep in mind is the terms absolute and global are interchangeable. Depending on the publisher of the textbook or the writer of the material, one may prefer the term absolute while the others may prefer the term global, but they do refer to the same thing. If we take a look at the graphs below, notice how some graphs do not have absolute extrema, while some may have an absolute maximum, an absolute minimum, or both. The first graph that we have here, which is of x cubed, has no absolute maximums or minimums. Our next function, we can see, does have an absolute maximum of 1 at x equals 0. However, because our function, which would be f of x equals 1 over x squared, approaches 0 but never actually becomes 0, then we will not have an absolute minimum. Keep in mind that yes, 0 is a lower bound of our function on the domain of negative infinity to infinity. But since our function does not take on the value of 0, then 0 cannot be the absolute minimum value of the function. As for our next graph, we see it has both absolute maximums and absolute minimums. Our fourth graph, we can see, has an absolute maximum of 2. However, it has this open dot here at x equals 2. It may be very tempting to say that negative 2 is the absolute minimum of this function. But because it's an open circle, the point 2, negative 2 is not part of the graph. Our function is getting closer and closer to negative 2 as x approaches 2 from the right. However, just like the horizontal asymptote in the second graph, we don't actually obtain that value of negative 2, so we cannot say it's the minimum value. In the fifth graph, we see that it does have a minimum and a maximum value. It has a minimum value of 0, maximum value of 4. And finally, the last graph does have a minimum value of 0, but because it has a vertical asymptote and is appearing to approach infinity as x approaches 2 from the right, then it does not have an absolute maximum. So one of the challenges is, how can we find the absolute extremum? One of the challenges to finding the absolute extremum is determining whether or not they exist to begin with. The extreme value theorem will give us criteria that are necessary to guarantee that our function has an absolute maximum and an absolute minimum. If f is a continuous function over a closed bounded interval ab, and here by closed and bounded interval we mean a and b are numbers, infinity is not part of this interval, then there is a point in ab at which f has an absolute maximum over the interval ab, and there is a point in ab at which f has an absolute minimum over AB. So to unpack this theorem, in order to guarantee the existence of absolute extrema, I need our function to be continuous and the domain of the function that we're considering to be a closed bounded interval. If we look back at the fifth graph, you can see that that function was a polynomial on a closed bounded interval. So according to extreme value theorem, there's an absolute maximum and an absolute minimum. But what happens when we drop these conditions? First, focusing on the fact that our interval has to be bounded. If we look at the first two graphs, where the domain is negative infinity to infinity, the first graph had no absolute extrema, while the other only had one. So we can see that a bounded interval is necessary. However, it does have to be closed. If we look at our last graph, it had a domain of 0 to 2, open at 2. That is not bounded. That allows us to have a vertical asymptote. So having a closed bounded interval is necessary. However, having a closed bounded interval is not enough. Our third graph is on a closed bounded interval, but it's not continuous. This allows us to have breaks such as jumps within our graph. So in order to guarantee the existence of an absolute maximum minimum, our function must be continuous and it must be bounded. Now, it may be possible to have both relative extrema when you do drop these conditions, such as with our third graph, where we have the function of cosine x over the set of all real numbers. But the conditions of continuous and closed and bounded interval guarantees the existence of our absolute extrema. Even though most of our focus of this section is to build a process that will allow us to find absolute extrema, we need to start by discussing what we're going to call local or relative extrema. We say a function f has a local or relative maximum at c if there exists an open interval I containing c, where I is contained in the domain of f, and f of c is greater than or equal to f of x for all x in I. What this definition means, if we say consider this point here along the y-axis, if we're considering the entire domain of our function, the point that is currently highlighted is not the highest point of the graph, so it's not the absolute maximum. However, if I consider just this interval here, specifically within that window of our function, our highlighted point will be the highest. So relative to the points around it, that point highlighted in yellow is the maximum. And that's where the term relative or local comes from. Relative to the points around it, or in a little local neighborhood, my yellow point is a maximum. Now, this is in contrast to absolute maximums or absolute minimums, where we're considering the entire domain of the function. In local, we're just considering a small part, a small window within the domain of the function. Looking at the graph, this point at the sharp corner is also a relative maximum. Yes, it is the absolute maximum, but by definition, relative to the points around it, it is the highest point. Our next term is local or relative minimums. A function has a local or relative minimum at C if there exists an open interval I containing C, such that I is contained in the domain of f, and f of c is less than or equal to f of x for all x and I. If we consider the point down there at x equals 1, it is not the absolute minimum point of our graph. In fact, our graph does not have an absolute minimum at all. If we consider this interval highlighted in green, then the points from that interval contained in that box we can see are higher than the highlighted point. So relative to the points around it, my yellow point is lower than everything else around it, making it a relative minimum since it's the lowest point relative to the points around it. Now we're going to discuss how to find local extrema. Before we do so, we need to talk about critical numbers. We'll let C be in the interior of the domain of f. We say that C is a critical number of f if either f prime of c equals 0 or f prime of c is undefined. The point C, f of c, is referred to as a critical point. One thing to keep in mind is this naming is kind of fluid. The terms critical point and critical number is often used interchangeably. You may hear me refer to critical numbers as critical points or vice versa. I'm oftentimes referring to the same thing. One of the reasons why critical numbers are important comes in from Fermat's theorem. If f has a local extrema at c and f is differentiable at c, then f prime of c equals 0. This theorem tells us that the possible locations of extrema will occur wherever our derivative is 0, as we see here in the first picture where we have a local maximum, or wherever our derivative is undefined. Because it includes f being differentiable at c, anywhere where our function is not differentiable could also potentially be a local extrema. As we can see here in pictures B and C, where we have the sharp points, but we still have local maximums and minimums at those sharp points. One thing to keep in mind, just because a function has a derivative of 0 at a point, or the derivative is undefined, does not guarantee the existence of a local extrema at that location. If we look at picture D, point C has a horizontal tangent line, or f prime of c equals 0. But we can clearly see that C is not the location of an extrema. Same thing goes with E, where we have a vertical tangent, meaning our function is not differentiable at C, but at x equals c we do not have a local extreme. Even though we can't guarantee the existence of local extrema at our critical numbers, it at least gives us candidates of where to check for local extrema. Now we're going to discuss how to determine when a critical point is a local extrema. This process that we're going to learn is referred to as the first derivative test. Now the first two steps are how we are going to find our critical numbers. So if we let f of x be the function 1/5 x to the 5th minus 4/3 x cubed, if we want to find the critical numbers, then from step 1 of the first derivative test, first we need to differentiate our function. Thanks to power rule, the derivative of our function is x to the 4th minus 4x squared. Now that we have the derivative, step 2 is for us to find the values of x that make our derivative 0 or undefined. As a personal preference, I prefer to find where our derivative is undefined first. Oftentimes, this is the step that most people forget to do when locating critical numbers. Here, our function is a polynomial. Polynomials are differentiable everywhere, so our derivative is never going to be undefined. So now we'll turn our attention to where our derivative is equal to 0. So now we'll set our x to the 4th minus 4x squared equal to 0. Then we'll factor our polynomial, and we get x equals 0, -2, and 2. One thing to keep in mind, just because you make your derivative 0 undefined does not automatically make you a critical number. At this point, these numbers that make our derivative 0 or undefined are going to be referred to as partition numbers. What makes partition numbers critical numbers is when they lie in the domain of f of x. Now here, because our function is a polynomial, and a polynomial has a domain of all real numbers, then all three of our partition numbers, 0, -2, and 2, are critical numbers. So we could potentially have local extrema at x equals 0, -2, or 2. Now that we know what our critical numbers are, we can now proceed to try to determine which of those are local extrema. In step 3, we're going to plot all the partition numbers we found in step 2 on a number line. One thing to be careful of is it's not just the critical numbers that need to be plotted. It does have to be all of the partition numbers, whether they're critical numbers or not. However, I would suggest marking the critical numbers. So I'll label them as critical numbers because the critical numbers do have the potential to be the local extrema. And we're going to use this number line to create our sign chart of our derivative, which was x to the 4th minus 4x squared. The sign chart was what we used back in Unit 1 to find the domain of a function that involved a radical. So if you recall, to make our sign chart, we're going to take sample numbers within each interval that is formed by our partition numbers and plug them into the derivative. Then we're going to determine if that value would be positive or negative. For example, for values of x less than -2, we could pick x equals -3. If we plug -3 into our derivative, we get a positive value. For x between -2 and 0, we can pick x equals -1. If we plug x equals -1 into our derivative, we get a negative value. Between 0 and 2, we can pick x equals 1, plug that into our derivative, and we get a negative value. And finally, for values bigger than 2, we can pick x equals 3, plug it into our derivative, and we get a positive value. Note that thanks to the intermediate value theorem, we can pick any value as our sample number within each interval. This is because we've already figured out all of the partition numbers where our derivative is either 0 or undefined. So within each subinterval, our derivative can only take on one sign, either positive or negative. Now that we've constructed our sign chart, we can determine where our function has a local maximum and a local minimum. Local maximums are going to occur at critical numbers where f prime of x changes from positive to negative. If we look at our sign chart, notice how around x equals -2, our derivative changes from positive to negative. Wherever our derivative is positive, that means our function is increasing. Wherever our derivative is negative, our function is decreasing. So a switch from positive to negative means our function is switching from increasing to decreasing, which we can see will create a relative maximum. So our function will have a relative maximum at x equals -2. Our function is going to have a relative minimum whenever our derivative switches from negative to positive at a critical number. If we look at x equals 2, we can see our derivative switches from negative to positive, which means our function changes from decreasing to increasing, which we can see will create a relative minimum. So our function has a local minimum at x equals 2. As for the values, to find our local maximum value, we will take the locations of our relative maximums and plug them into our original function, not into the derivative, the original function. This is because we are discussing a behavior of the original function now. Plugging -2 into our original function, we get that the value of our local maximum is 64/15. Doing the same thing for our local minimum, we'll plug f of 2 into our original function, and we get -64/15. Since the sign of our derivative did not change around x equals 0, then x equals 0 is neither a relative minimum nor a relative maximum. Next, we're going to find the critical numbers of f of x, which equals 1 minus 2x squared over 4x to the fourth. To start, we do need to find our derivative f prime of x. To find our derivative, we do have to use quotient rule, and after applying quotient rule, we get -4x times 4x to the fourth minus 1 minus 2x squared times 16x cubed. Since we do want to set our derivative equal to 0 or see where it's undefined, we do want to try to simplify our derivative as much as possible. Not only do we want to simplify our denominator, but ideally we do want to try to factor the numerator and denominator as well. Right now, we could go ahead and start expanding the numerator, but it's always a good idea to try to find common factors first, so that way we can factor them out and make the simplifying easier, and at least have one step in the factoring process complete. If we focus on the 4x to the fourth and the 16x cubed, we know that they both have a 4x cubed as a common factor. So in the numerator, let's go ahead and factor that out first. And that'll make our numerator 4x cubed times the quantity of -4x times x minus 1 minus 2x squared times 4. To simplify our denominator, we can square the 4x to the fourth, which is 16x to the eighth. Notice that the 4x cubed and the 16x to the eighth will reduce each other, leaving us with 4x to the fifth in the denominator. As for the numerator, we can multiply the -4x and the x together in the first term, and in the second term, we can distribute in -1 and 4, which makes our numerator -4x squared minus 4x plus 8x squared. Then we can collect our like terms, and our numerator will simplify to 4x squared minus 4, which we can further factor to 4 times x minus 1 times x plus 1, and we can see that the 4's cancel. So our derivative would simplify to x minus 1 times x plus 1 all over x to the fifth. Now we can find our critical numbers. We'll start off by finding where our derivative is undefined. Since our derivative involves division, then we want to see when our denominator x to the fifth equals 0, x to the fifth equals 0, when x equals 0. X equals 0 is a partition number, but is it a critical number? If we plug 0 into our original function, we can clearly see our denominator will be 0. Therefore, x equals 0 is a partition number, but it is not a critical number. Next, we'll see where f prime of x equals 0, which means we're going to set our function equal to 0. We'll multiply both sides by x to the fifth to cancel out the denominators, and we have to solve x minus 1 times x plus 1 equals 0. And this is why we wanted to factor in our derivative, not only to get rid of the common factors, but now it's really easy to solve for x. We can see that 1 and -1 would be the solution to our equation. If we plug 1 and -1 into our function, it will not make our denominator 0, so our only critical numbers are 1 and -1. Now we're going to find our local extrema and the values of the local extrema. Just like our last example, we're going to make our sign chart for f prime of x, which is x minus 1 times x plus 1 all over x to the fifth. Remember from the procedure, we're not just placing the critical numbers on the number line. We're placing our partition numbers on the number line. This would include 0, which we know is not a critical number. So 0, 1, and -1 all go on the number line. Out of the three, only -1 and 1 are critical numbers. They are our only candidates for the local extrema. From there, we'll fill in our sign chart, picking values within each of our subintervals and plug them into our derivative. And our sign chart from left to right would be negative, positive, negative, positive. Now for our local maximums, that is where our derivatives change from positive to negative. It's very tempting to say that x equals 0 is the location of a local maximum, since our derivative changes from positive to negative. However, 0 is not a critical number since it's not in the domain of our function f of x. Therefore, 0 would not be the location of any local extrema, no matter whether or not there's a sign change or not. If we look at 1 and -1, they're switching from negative to positive, so they cannot be local maximums. So our function has no local maximums. As for local minimums, we do see at 1 and -1, they both have our derivative switch from negative to positive. So both 1 and negative 1 would be the location of local minimums. To figure out the values, we'll plug negative 1 and 1 into our function. F of negative 1 and f of 1 are both negative 1/4. So keep in mind, only critical numbers can be local extrema, which is why it's so important to label the partition numbers that are critical numbers. Second, it is possible when we have multiple local maximums or local minimums for us to have different values of those local minimums and maximums. So make sure you're being thorough after you have determined whether or not a critical number is the location of a minimum or maximum, that you plug them into the original function and present all possible values of our local minimums and local maximums as answers. Now that we've discussed how to find local extrema, now we can talk about absolute extrema. In order to find absolute extrema on a closed interval, it would be impractical for us to just plug in every number within that closed interval since there's infinitely many. However, it turns out that our absolute extrema can occur at one of two locations. They could either be located at relative extrema or at the endpoints of our intervals. So now we can discuss our procedure. We'll let f be a continuous function defined over a closed interval ab. So in our example, we're going to use f of x equals x squared minus 3x to the 2/3 over the interval 0 to 2. The first step is we're going to find all critical numbers of f that lie within our interval. The reason why we want to find the critical numbers is they have the potential to be the relative extrema. So just like what we did in previous examples following step 1 and 2 for the local extreme process, we'll start by differentiating our function, and our derivative would be 2x minus 2x to the negative 1/3. Since we need to see where our derivative is 0 or undefined, we will first rewrite our x to the negative 1/3, so that way the power is positive, and rewrite the 1/3 power as a cube root. Now we'll determine where f prime of x is undefined. F prime of x is going to be undefined when the cube root of x equals 0 or when x equals 0. 0 is within the domain of our function because our function is continuous over the interval 0 to 2, so it is a critical number. However, it's not in the interior of our interval. We want it to be strictly between 0 and 2. So 0 we're not going to consider as a critical point that lies in the interior of the interval 0 to 2. Whether you cross out 0 or not as a critical number is up to you. We are going to have to plug in 0 anyway, as we'll discuss in step 2. We'll set f prime of x equal to 0, so we have 2x minus 2 over the cube root of x equals 0. There are several different ways to go about solving the equation here. It's up to you how you wish to solve. What I would do is first add over the 2 over cube root of x, treat the 2x over 1, and cross multiply. 2x times the cube root of x is x to the 4/3. 2 times 1 is 2, and we get x to the 4/3 equals 1. To get rid of the 4/3 power, we'll raise both sides to the 3 over 4th power. Now 1 to the 3/4 is positive 1. However, raising both sides to the 3/4 power is equivalent to cubing and then taking the 4th root. The 4th root is an even root, so we do need to remember the plus or minus. If the denominator of the power we're raising both sides to was odd, we wouldn't have to worry about a plus or minus. However, keep in mind, we only want the critical numbers between 0 and 2, which is the interior of our interval. Since negative 1 is not between 0 and 2, we would throw that out, leaving x equals 1 as our only critical number for step 1. Now that we've found our critical numbers, we can move on to step 2. Step 2 is to evaluate our endpoints, which would be f of a and f of b, and the function at each critical point that we found in step 1. So we need to find f of 0, f of 1, and f of 2. F of 0 and f of 2 is because we need to evaluate our function at our endpoints. F of 1 is because 1 is our critical number. Plugging each value into our function, we get that f of 0 equals 0, f of 1 is negative 2, and f of 2 is 4 minus 3 times the 4th root of 4. Now we're going to determine out of these possible values, which of them would be the absolute maximum and which would be the absolute minimum. The largest among these three values would be the absolute maximum, while the lowest of these values would be the absolute minimum. If we take a look at the 4 minus 3 cube root of 4, if you are not sure an approximate value for it, you can punch that value into a calculator to approximate, and 4 minus 3 cube root of 4 is approximately negative 0.76. Now that we've made it easier to compare, we can see that 0 is the maximum value, and negative 2 is the absolute minimum value. Notice that we didn't have to make a sign chart to figure out whether our critical numbers are relative mins or maxes. We're just using the critical numbers to narrow down the possible locations of our absolute max and minimums. Once when we plug every candidate for the location of our absolute max and minimums into our function, we can just directly compare which is the highest, which is the lowest.